call it the personal atmospheric dome, or the pad. And here's the thing I think people miss is that this is not a theory. It's not an idea. It's the truth. It's a fact. And you can figure that out on your own by just simply knowing that if you look up, that's the least amount of atmosphere that there is right above you, straight above your head. So if any light is coming directly down from straight above you, that has the least amount of refraction. It has the least amount of effects. Those rays are going to come at you parallel if the sun's right above you. And then if you look to your left or right, or straight ahead of you or behind you, that is the most amount of atmosphere. So right away, you can tell if the least amount of atmosphere is above you and the most is to your sides. That creates a personal atmospheric dome. We all see through it. No matter where you're at on the Earth, no matter North Pole, South Pole, wherever you might be, you exist inside of a personal atmospheric dome where everything renders to you. So nothing can just appear in the sky. It all has to come from far away. So that's why we see things come up from the horizon line, right? And so this is a dome. We see as a dome. And if you think of the sky being a plane above you, so a plane of stars above you, as things get further, since you're looking through more and more atmospheric distortion to see them, things appear to bend down towards the horizon line. And so that's the personal atmospheric dome. And when you understand that, and you realize that no matter where you're at on Earth, you see the sun rise to the east of your personal atmospheric dome and set in the west. And so people get very tripped up and they say, well, what about in the south? Isn't it the opposite? Where it's just, no, they are looking north. And so things rise on their right and set on their left, whereas us in the north, we look south and things rise on our left and set on our right. So it is a personal atmospheric dome. And then you have to learn to understand that. So many people get caught up in the idea of here's the fooling part. You live in a personal atmospheric dome. That's what you live in. That's what you see things through. They convince the world that there is another personal atmospheric dome below you with somebody living upside down inside it. And that's the biggest, fooling point of the entire thing is that, no, you exist in your personal atmospheric dome. That's how you see things. When you watch a plane fly off into the distance, it doesn't just fly straight up and then disappear into the clouds. It goes down towards the horizon. That's the way everything works. Just like the sun sets, just like the moon sets, just like the sun rises, just like the moon rises, just like a plane coming over the horizon, as you might term that, but just means it's coming from far away. I can't see planes from where I live leaving the San Francisco airport. It's too far. But as things get closer to me, I would see them appear not out of the middle of the sky, but from the horizon line, because it's finally rendering itself to me. It's big enough to come into my personal atmospheric dome. And that's the way the entire world works around you. It's hard to explain, I guess, the personal atmospheric dome for people to get, but one visual that I thought was really good is if you picture a really foggy day, so it's extremely foggy, and you're at a train station and you're reading the train schedule, and you would only be able to see, let's say, you can only see your own train schedule. You're looking at it, and if you look any further, it's too foggy to see. So, but if you think about there being 10 other people at this train station at the same time, and everybody's looking at their own little document, well, they can read their own little train schedule, but to all of them, they can't see the other people around them. That's how the Earth works. That's how our atmosphere works. Same thing when two people on flat Earth are standing near each other, maybe 4 or 5 miles away, but to each other, the horizon ends before you can see the other person.
I don't know if you guys have seen this. Shout out to Flat Earth Awakening. And believe it or not, to Walter Bislin. I'm sure you guys know who he is. If you don't, well, you'll probably catch him in your comments section at some point. But I want to play this video. It's 3 minutes and 45 seconds. Actually, it's mostly music, so I'm just going to mute it. There's only one part that has any audio. But what this is this is taken from Walter Bislin's Flat Earth Modeling app. And what it does is it shows the personal atmospheric dome and how it works. Now, I have to remind you guys that Walter Bislin is a ball earther, right? He is absolutely not a flat earther. He thinks it's silly. He's battled, in several comment sections. He battles Flat Earth FE Core. He's just really a baller. And what's amazing is he has come out with this app, and it shows precisely what we have been talking about this personal atmospheric dome, right? And this is, very similar to P-Brain's graphics, but it shows the sun and the moon rotating above a flat Earth, and with our personal atmospheric dome, how it actually is perceived by us. And it's really quite an amazing app, and you can actually go there and play with it on his webpage. But I just want to let this run a little bit so you can see actually what's happening here. You can see the continents and how, or I'm sorry, you can see the stars and how that you're perceiving them. If you move latitude, anywhere in the latitude, you can see, of course, that personal atmospheric dome then starts turning on its side. Until you get to the equator, then it's pretty much equal. And that is, of course, when we've seen all of that star trail footage that splits off in two different directions at the equator. And then if you continue further south, the personal atmospheric dome kind of starts tilting back up at an angle. So the one thing about this also that I want to point out is not only does this back up 100% what, Jaron has talked about and a lot of flat earthers, but it also backs up 100% exactly the idea of how an EQ mount on a telescope can work. Just like we said before, when you are dealing with optics and we have a personal atmospheric dome, and it doesn't matter if we're looking at it with our eyes or a camera is looking at it, if you set up a telescope and calibrate it to either the South Pole, South Celestial Point, which is not a star, or North Pole or Polaris, calibrate it, and then you follow any of these grid lines around, it follows and tracks absolutely perfectly on a flat Earth. And in fact, beyond that, if you really start thinking this through, and this is the one thing that the ballers never, ever, ever want to take into consideration in their models, is how you see how our perspective actually works. They're always trying to use these orthographic type views, side-on views, and do all their math and geometry from that. Well, great, and it works that way, but unfortunately, we don't see the world that way, right? And neither do telescopes, ladies and gentlemen, okay? So what this not only proves is that the telescopes, the EQ mount telescopes can work and do work on a flat Earth. But if you think about it, if that same personal atmospheric dome is then applied to a ball Earth, then the EQ telescope will not work at all. Okay, think about that for a while, guys, because you've got basically a double whammy there. You're going down the latitude of the globe, which is what they say the scope is tracking. However, at that point, they are assuming absolutely no personal atmospheric dome. And if you were to factor that in, it wouldn't work at all, plain and simple. So, at this point, I think I'm almost obligated to ask the ballers to prove to us using atmospheric and our perspective in a personal atmospheric dome how an EQ mount telescope could possibly work on a globe.
Hello everybody, Steve Matthews here, and today we're going to talk about field rotation and its errors. I can be found on YouTube under Teeth of the Lamb, all one word, or on Facebook just under Steve Matthews. If you've been following my videos, you would know that I've been filming the moon recently and looking at the rotation, the clockwise rotation of the moon throughout the day. I've been trying to fit the rotation of the moon into the heliocentric model and, using all of their distances and rotations, and quite frankly, I just can't seem to fit it into that. And the problem is that if you have an object that is 2,159 miles wide in orbit, 239,000 miles away, you just quite simply don't have a big enough arch to create field rotation. The face of the moon will exhibit about 180-degree turn in one day. Now think about this for just a moment. To get a half a turn, 180 degrees on that moon, you have to have a very drastic arch across from horizon to horizon. And there just simply isn't enough at 239,000 miles away. The radius of orbit is so large at 239,000 miles that it would be practically imperceivable to have any kind of rotation on that moon, anything visible anyway. So I figured there must be something that I don't understand or know about field rotation. So I went online, watched a number of YouTube videos on the topic, you know, lectures and stuff, college level, and it became apparent real quick what the problem was. And simply put, they've gone too far. They've made everything, their wild, fantastical millions and billions of miles is just simply too big to support any form of arch whatsoever. So they have to pull everything back, right back to the dome. Okay, so let's think about this again. You know, they like to push this, that you can't see the curvature of the Earth because it's just simply too big. Okay, let's take this. Our nearest star is Alpha Centauri A and B. It's a set of stars. And you've got that at 4.3 light years away. To put that into perspective, that's light traveling at 186,282 miles per second for 4.3 years. Now the problem is the heliocentric model would dictate that you have to draw your orbit at that 4.3 light years away. And they just simply can't do that because they won't have any arch, and it's unexplainable. So they have to pull everything back to a very close proximity to the Earth. And it would be just like God said, that he put the sun and the moon and the stars in the firmament right over our heads. And that's exactly where they have to place them. And they spend a lot of time trying to justify that. Well, we can't tell how far things are away, and we have to do a lot of tricks to get our distances. No, the sun, the moon, and the stars are not far away, and there is nothing that is obvious that says that they are, except one set of people. And that group of people would be the heliocentric cult of scientism. The same group of people that would be all too eager to point out that our forefathers were morons because they thought the Earth was stationary and flat with a dome over it. And all the stars, the sun, and the moon were placed in that. So they built their house of cards on lies and deceit, with placing everything millions and billions of miles away, and they're oh so clever. But the real funny part of all that is that they've had to take the work that was built on the backs of those morons, and they had to plagiarize it and use it for their own, because those distances just absolutely do not work in field rotation. So you have to pull them back. You have to pull them right back to the dome where God said it was. And that's my point. The distances used by heliocentrists is impossible to create any form of arch that's steep enough to give you field rotation. They like to do this distance game with everybody, where they change the distance real far away at their convenience, and they pull everything way back at their convenience, and everybody's just supposed to buy it. But you know, those distances are, in an equation, the biggest part of it, and you can't ignore it, and you can't get by with just saying, oh, well, we just can't perceive those distances. Well, you have to be able to perceive them, because you can draw a circle that's a straight line, and that's what you'd end up having, and you wouldn't see any field rotation. So don't let them keep playing this game with everybody. They did this during the total solar eclipse of 2017, where they pulled the sun 400 times closer to create a penumbra with the moon. Don't let them do that to you. When I was doing my brush up on field rotation, I watched a number of videos, and I took some clips out of those, and I'd like to show those to you. We'll have a little fun. Listen real carefully to their terminology and what they say, because it's pretty revealing, and actually I got quite a few laughs out of it. So I'm just going to let these play out for you, and I think you're going to enjoy it. Now pay attention, because they keep saying that our forefathers believed that there was a crystal sphere around the earth. And that's not true. They believed there's a crystal dome over the earth, and that's exactly what they have to portray here. And you're going to find that real interesting. One big proof video floating around on the internet is where they have the Blue Angels and they fly directly overhead at a low altitude, and they film it, and then they take 3 or 4 different photographs, one before it reaches them and one above and one afterward, and it shows rotation. The red, white, and blue contrails are pointed in different directions, showing that it's rotating. But this is my whole point. That's possible when you have something close at hand, but not when you have something distant and far, because you don't have enough arch. And that's the whole point of this. These clips are under fair use for commentary, critique, and review and discussion.
Hello ladies and gentlemen, and welcome back. I'm Mr. Stano, your Earth Science teacher, and today we're going to talk a little bit about the celestial sphere. The celestial sphere is the backdrop that everything appears in either the nighttime or the daytime sky. If you take a look, we have this little gentleman right here looking through a telescope, and all the stars appear to be on this right here, this dome that surrounds us. There's a couple of components. You can see that he stands in the middle. The observer always stands in the middle of their celestial sphere.
The celestial sphere is an imaginary sphere surrounding the Earth, onto which are projected the objects of the night sky.
How the sky moves. Look up on a clear night and you'll notice that the sky looks like a vast dome with stars fixed to its inner surface. The Earth spins in space, rotating once a day on its axis. But from an observer's point of view, the Earth appears to remain still, while the celestial sphere seems to rotate once a day around an axis that runs from the north celestial pole to the south celestial pole.
Okay, so this is a model of the celestial sphere, and it's really hard to get an idea of what's going on without seeing it, and I can't even tell you if this is showing up the camera because I covered up the video because I can't seem to see myself. Just to let you know. So the goal of the celestial sphere is to somehow picture the sky, and in this model it represents all the stars as being on this shell surrounding the Earth. Now clearly that's not the way it really is.
Since the planets in our solar system orbit our star largely on the same plane as each other, kind of like a giant pizza with the sun in the middle, the path of the moon and planets in the sky closely follows this line of the sun.
Celestial sphere typically is shown as a clear globe, plastic or glass, and the Earth is at the center, and the stars, sun, moon are all about the sphere as we see them in their constellations. Of course, this is not real. It's only convenient. It's a convenient way to talk about the sky.
This video, taken from a mountaintop in Chile, where some of the world's largest telescopes reside, shows this motion of the sky, but time has been sped up. At these speeds, and with a little imagination, it is easier to think of ourselves as passengers on spaceship Earth, spinning against the background of fixed stars. In general, though, our senses make it hard to accept that the Earth is moving at all, and we are moving very fast. At the latitude of Tucson, we're moving at 880 miles per hour. But we just don't sense any apparent motion. In fact, as you will see in a later lesson, it wasn't until recently that the notion of a rotating Earth became commonly accepted. It's much easier for us to instead imagine the entire sky rotating around us, since that is what we observe with our senses. We see the sun rising and setting, and stars moving across the sky. Because the Earth is a sphere, we represent the sky as a celestial sphere surrounding the Earth.
Okay, well, Going back to this idea of the celestial sphere, let's start by taking the Earth's poles and projecting them onto the sky, and that gives us the north and south celestial poles. And we'll take the Earth's equator and project that onto the sky, giving us the celestial equator. So this, in total, is the celestial sphere. Now, we know today that, no, the stars are not really imprinted on an actual sphere, but it's a useful fiction. It allows us to identify not only the positions of stars in the sky, but to help us understand their apparent motion around us.
Celestial sphere. Well, as an observer on Earth, if you look at the night sky, you will see that it appears as a huge dome or sort of inverted hemisphere.
Now, we've talked about this already in class, but what I wanted to talk about also is that yellow sphere that's inside of here. That's really where we left off. Now, that turns out to be a model of the sun. And we know that the sun is much bigger than the Earth, but in this particular model, it's actually quite small. I mean, after all, when you look at the sun in the sky, you can put the sun behind your finger. So its angular size is actually quite small. It's a big object, but very far away, obviously.
I have to make commentary here. There's nothing obvious. I see a small, close sun, and nothing is obvious about a sun 1,300,000 times the size of the Earth, or 93 million miles away. Nothing obvious at all.
It's based upon our lack of understanding of distance. Like when you look up at the sky at night, can you see how far the stars are from us? No. We have no idea how far they're away.
Excuse me? We have no idea how far the stars are away? NASA has a distance to everything, even the weight. Hey everybody, listen real carefully to all of the excuses they're given for this field rotation.
Distance is the hardest thing to measure in astronomy. We have to use all sorts of tricks to figure out distances. Just looking at the sky, we have no comprehension of distance, or that some stars are farther away than others. They all appear to be kind of at the same distance. In fact, this is what the ancient models, cosmological models, assume. The ancient models assume Earth is sitting here at the center, and then around it there is a sphere. They didn't think of the stars as distributed through three-dimensional space. They thought there was a sphere that enclosed the Earth. They call it the celestial sphere. But imagine the sphere encircling the Earth, and you can do that. Since we can't see distance, we can pretend they're all at the same distance, painted onto this sphere. And, back then they thought the Earth was standing still, and the sphere would actually go around the Earth. The whole universe would go around us. Nowadays we know that under the idea of the sphere, the universe is out there and we're rotating underneath it. Makes the appearance of motion of these stars.
In this video, we'll explain the coordinate systems used in celestial navigation. Every location on our planet has a unique set of terrestrial coordinates consisting of latitude and longitude. These are more commonly referred to as geographic coordinates. Let's assume our planet is a perfect sphere.
The celestial sphere is the imaginary crystalline sphere on which all of the stars exist. The Earth is the center of the celestial sphere. So we get this idea back from the Greek times when they actually used to think that stars are on a crystal sphere.
Actually, they never thought it was a crystal sphere, but thought it was a dome. Our forefathers knew about a flat Earth and a dome.
Okay, but of course now we know that that's not true. Stars, no matter how distant, they are pictured as being on a single crystal sphere. So bring them down, and then now state where are they located on that sphere, you see? So even though the concept of a sphere, a crystal sphere is not true, as a scientific model, it's still a helpful model to write down where stars are in the sky and how they travel in the sky. So it's a good scientific model.
This model explained why all the celestial objects moved in the same direction at the same speed. It also explained why the stars remained in fixed positions relative to one another. The Earth-centered or geocentric model of the universe was used successfully for thousands of years to explain most of the observations of celestial objects. Even though we now know that the motion of celestial objects is due to Earth's rotation, it is still sometimes useful when discussing objects in the sky to think of them as part of a sphere surrounding the Earth. The most that an observer would see at any one time would be half of this sphere, but we still refer to this imaginary half sphere or dome visible over our heads as the celestial sphere, even though we know better.
On the celestial sphere.
Okay, before we show you how to find the North Star, let's point out a few things. First things first, this is not how all the stars are not actually on a sphere around the Earth.
Greetings and welcome to the Introduction to Astronomy. In this section we will talk about the celestial sphere, and that is really what you see when you go out at night or during the day and look up at the sky. It looks like the universe is a great sphere surrounding the Earth, and that is what ancient astronomers would have believed. And when we look out at it, it still looks like everything is stuck on this great celestial sphere because we don't see the three-dimensional nature of the universe. You can't tell when you look at various stars whether they are close or far away. There are measurements that astronomers can do to tell that, but in reality what everything looks like is like it's hanging on this great celestial sphere that we will talk about today, because we still use that for determining locations of objects on the sky. So what is the celestial sphere? Celestial sphere is a way of visualizing the sky. So it is a way that we're able to see what there is in the sky, and it is a geocentric model. What that means is that we are looking at it from an Earth-centered point of view. So that is Earth-centered here. That we are looking at it is essentially, we consider it Earth-centered. Now we know that's not correct.
Let's assume our planet is a perfect sphere.
But it still works for determining positions in the sky because it acts as though we are at the center of this great sphere.
Let's assume our planet is a perfect sphere. Let's assume our planet is a perfect sphere.
And all of the stars, all of the planets, all of the other objects that we see, things like galaxies, all appear to be positioned at various points on the celestial sphere. The planets, the name comes from wanderer, so they are wanderers. They wandered among the stars and moved through the stars. So in the image here, you can see that the planet here is moving through Capricorn and then moves into Aquarius. It makes a little loop and then it comes back and heads into Pisces. This is what we call retrograde motion. This little loop, this is something that is distinct to the planets only. So only planets will undergo retrograde motion. The sun and the moon do not do this. They move through the sky just like this. They go through those constellations, but they just make a completely straight path. The planets will at specific times form this little loop, which was very important for our understanding of the motions of the planets.
Just to highlight some of the things we've talked about here today, the field rotation requires pulling all of the stars, sun, and the moon within a real close proximity sphere. And they have to do that because if they use the actual distances, the arc of the moon and of the sun and of the stars would be so large that you wouldn't see any arc or field rotation, because that's what causes the field rotation. They'll start saying that they can't tell the distances to the stars, and they'll say that it's all an illusion, that you couldn't perceive the distances, so they have to pull them real close. That's their excuses, but there's a dome over this Earth, and they had to put those stars and the moon and the sun right back where God put them, where he's to cover their lie. They can't account for the great arc that it takes to rotate the moon and the stars as much as they do without making them real close. I'd like to ask each of you to pay very close attention to these meteors as they traverse from horizon to horizon in an absolutely straight line without any atmospheric distortion or atmospheric lensing, no refraction or bending of their trajectory at all. It's significant to point out that these meteors are said to be skipping along the outer edges of the atmosphere, and as they do, they light up. So if we were ever to see a really good example of refraction or lensing or any of these distortions that are so talked about, we would expect to see them the most from these meteors that are skipping along the outer edges above all of our atmosphere. Yet we see zero, nada, none, no distortion or bending of the light at all. According to the predominant way of thinking, we would expect to see the most bending and distortion at the horizon. Yet again, we see none. I like to drive this point home because this distortion is used for so many excuses, and one being the shuttle launches. I suppose all of you remember this, an arch when they're trying to shoot straight up into space, and would like to have you believe that it's an optical illusion when it's nothing of the sort. If it were true, we would see distortion in those meteors, by all means, being on the outer edges of the atmosphere. Let me be clear here that I'm not saying that atmospheric distortions don't exist. I'm saying that they don't exist to the degree and are not the excuse for a lot of the things that we see. Under the right conditions, yeah, you can have distortion. I'm a firm believer in what I see is real until I have a good reason to believe otherwise. The psychological warfare and the intellectual fraud portrayed by NASA when they tell you that they're going straight up into space and they show you pictures like this. Well, I'm calling BS on this right now. Especially when we can see meteors traversing the outer edges of the atmosphere from horizon to horizon and exhibiting no distortion whatsoever, as straight as an arrow, even down on the horizon. That's a telltale sign that we're not being told the truth once again. The things we see are not illusions. And we've been way too gracious with those people that are trying to make us believe that they are. In just a moment, I'm going to play a short clip from Science Monkey, the celestial sphere, and basically all the celestial sphere is the visible sky, which is actually the celestial dome, and they've added another side to it since the heliocentrics have taken over. It's all a geocentric model, which means that the Earth is not moving. All it means is just what we see in the arch of the sky from horizon to horizon. And today we're going to be talking about that. We're going to talk about what we should see if all of the sun, moon, and stars were as far away as they say. One last point that I'd like to make here about the distortion is that when you look out on the horizon and see a supermoon or a very large moon, you'll see the moon is increased in size, but the stars around it, they haven't changed. And I don't know what that means, but it's significant, I think. These pictures of the Milky Way galaxy are just absolutely stunning. And I'd like to play just a little bit of it here for you because they're just beautiful. That's all I can say. And then we're going to talk about the arch of our visible sky and the path that the sun and the moon and the stars should follow. They shouldn't all follow in the same path. And I might be corrected on that, but I'm going to explain that in detail here after Space Monkey gives a 1-minute presentation on our celestial sphere. Every time I start looking at a different topic that NASA or the schools are teaching, it crumbles under just very little observation and very little scrutiny. Just a little thinking and nothing works out. Numbers don't add up, things don't make sense, and they keep telling you that you don't need to worry about distances, and I think distances are quite important because we're talking about vast distances, and that becomes very important. Okay, here we go, on with our topic, field rotation and its errors, part 2, before I bore everybody.
Hello ladies and gentlemen, and welcome back. I'm Mr. Stano, your earth science teacher, and today we're going to talk a little bit about the celestial sphere. The celestial sphere is the backdrop that everything appears in either the nighttime or the daytime sky. If you take a look, we have this little gentleman right here looking through a telescope, and all the stars appear to be on this right here, this dome that surrounds us. There's a couple of components. You can see that he stands in the middle. The observer always stands in the middle of their celestial sphere. And we have our directions down the bottom. We can see north, south, moving this way, east, and west right here. All the stars, everything appear, it appears two-dimensionally to be surrounding us. So when you look up in the sky, it doesn't matter if it's a plane, if it's stars, the sun, anything, any other satellites that we see, that's all appearing on the celestial sphere.
So I put together a little illustration to help explain what I mean when I say that you'd have 3 different angles of arch traversing the sky, one by the moon, one by the sun, and another by the stars. Think of each of these as having their own personal orbit, and the moon would have one orbit, and the sun would have another, and the stars would have another yet, and each one of them vastly further away. And as you increase the size of the orbit, you increase the size of the circle and or the arch. In our observable sky, all of the celestial bodies follow basically the same path. And what I'm saying is that's not possible if they're vastly different distances away. The astronomers and the scientists and the teachers will tell you that distance doesn't matter, that we can't tell how far away these items are. Well, I have it all on my chart right there above. How far away everything is, they tell us that. And my point is that they have to bring everything back to one level plane, because that's where it is. It's in our firmament over our heads. And I'm telling you also that you can indeed tell how far away these items are by the path they take across the sky. The ever-increasing distances would demand that the arch, the circumference, gets larger, and your arch is going to be a lot smaller as you move further away. And we're not talking just a few miles. We're talking vast differences in distance. An example, I would suspect that most of you have played with a paint program or something on your computers. And you start, if you take a circle and you start enlarging it, you start out with a small circle, and pretty soon it's reaching the edges of the page, and you keep on going with it, and pretty soon it's off the page, and you've got an arch across your page, and you keep increasing it, and eventually all you've got is virtually a straight line across your page. And this is what I'm talking about. But that's a little circle. Now, when you start talking about increasing the circles by millions of miles, it makes the arch flatter, always. So we have here on my illustration the bottom where the dome is, and that would be where everything is placed in one sphere over our heads. And in that diagram, everything at the same distance would give you one arch for everything. Now we move up to the moon. It's 239,000 miles away, and they say that you would have to take your size of your Earth and multiply it by 30, and that would give you where the moon would be placed. That'd be a big circle, and it's not going to be much of an arch. And then we move up to the sun. It's 93 million miles away. It's 400 times the distance of the moon, so they say. That's going to make your arch much less steep. And then you move out to the stars. The closest star, Alpha Centauri, is 4.3 light years away, and that's 186 miles per second at the speed of light for 4.3 years. And I'm saying at that distance you'd indeed have a straight line. It wouldn't have any rotational arch that you see like in the stars. No, they have to bring everything back to a single plane for this very reason. So today we've learned that meteors and their skipping across the outer atmosphere can give us a good indication that the atmospheric distortions that we see are not as severe as what we're led to believe. We've also talked about distances do matter, and we can tell how far away the sun, moon, and stars are, because they all follow the same path. They must all be on the same plane, and we've discussed how you can determine that. We're taught in school that the sun is stationary, the moon is stationary. It takes 27 days or so for it to make one orbit around the Earth. So in an 8-hour day, it's moved very, very little in the sky. And they say the Earth is turning counterclockwise, and it overtakes the moon, which is also moving counterclockwise. So it moves about 5 degrees in the sky per hour. So for all practical purposes, the Earth is the only thing that's moving, and the sun and the moon are stationary. This is what we're taught in school. So the question that arises, if the sun and moon are stationary and the Earth is the only thing that's moving, then what we're seeing when the sun and the moon cross our sky is simply nothing but parallax. As I demonstrated in the short little clip in the very beginning of this video, that parallax is nothing more than when you're moving and you see a distant object such as a mountain, and all of the trees and things that are closer to you appear to be whizzing by. So the distant object appears to be moving much, much slower. And that doesn't work out very well when you apply it to the sun and the moon, because every day that I'm outside, I see the sun overtake the moon. And that doesn't work out right, because what should be happening is the moon should overtake the sun, and we don't see that at all. So the globe's got another problem, and we're going to look at that today. This day, when I got up, I started filming the moon as it rose, and it went up in the sky for a ways, and here comes the sun, and it completely overtook the moon. And as you can see, the moon's up in the sky here and the sun is setting. So from a perspective of parallax, I want the boys that have to set down the calculator, and I want them to take a ride with us in the car and see how Parallax works. And then I want them to go back in, sit on the couch, and play with their little balls and tell me how this works, and they can use their calculators. Why the sun is overtaking the moon from a parallax perspective. And I'll be waiting for their answer. So first, let's look at what a simplified orbital mechanics would look like. This is what we're taught in school. The Earth is rotating counterclockwise, and the sun is stationary, and the moon, for all practical purposes, is stationary as well. So let's take a ride in the car and see how this works. The distant mountains would be the sun, and the trees that are coming by would be the moon. What do you see going on here? What you see is the sun lagging behind, and you would see the moon overtaking the sun. And that's completely opposite of what we actually see in reality. Everybody has been outside and they've seen the moon rise, they've seen the moon being overtaken by the sun and setting. And if you haven't, you need to take another look. The developments so far to date, what we've noted is that the face of the moon rotates clockwise. The shadow moves as if attached to the moon, not independent, as it should if it were a cast shadow from the sun. The moon's face doesn't rotate at times, as noted in the January 20th lunar eclipse. The face of the moon jumps backwards, as also noted in the January 20th lunar eclipse, then by Richard, Mr. Thrive and Survive, on February 16th, which was just before the following full moon. The element of most interest and most significant to us at this moment is the backwards motion that Richard has detected by using 2 equatorial mounts and 2 different cameras. And on the 16th of February, he was able to film it having a jump backwards. And what I want to go over today is I have photos that I took on the 16th and on the 18th. And I believe that they actually show that jump backwards. And I'm going to go over that and explain why today. What we have here is the times the photos were taken. The first row is the February 16th, and the second row are the photos that I was able to take every hour on the 18th. And the third row is an overlay of the 16th and the 18th. Now I've gone back, dropped them back, and overlaid them an hour back, because Richard is in Phoenix and I'm on the coast of Oregon. Because the moon loses about 55 minutes each day, I've gone back 1 hour at first, and then I drop it back 2 hours because there's a couple days between. But each of them show that there's clearly a backwards motion to, I mean, it's counterclockwise and it should be going clockwise. So here we go. I'm going to move the overlay back and forth over the top real quick here so you can see how much clockwise rotation we've had on each of these by the hour. And starting with the February 16th photographs. Now I'll bring the one in front of it over this one, and you can see there's very little movement here. Very, very little, if any. This takes a minute to go through, but it's well worth it. That one just jumped back where it was. So I'm going to bring it forward now and put it over this one. And again, we just have a little dab of forward motion, maybe a eighth. Clockwise motion there. Now I'll bring this one back and go over it again. We've got about maybe a quarter of the Sea of Crises on the very top there. That's the crater I'm watching, because it's real good for detecting the motion of the moon. Now this one, you can see it's moved forward quite a bit. And this is where I think Richard detected that backward motion, even though it's not 1 hour difference. I still think that's where it happened. And the reason I think that's where the backward jump was is because at first I thought the moon was speeding up because it traveled a lot more distance in 1 hour than it had in the past. So, but now I'm of the mind that jump is causing it to go backwards, and then the rest of the hour it goes forward. So it's given me a larger gap between how far it moved, and that's how I'm seeing it. I think the moon is moving steadily forward in a clockwise rotation, but I think these jumps backwards may be happening more often than we think, because I've seen a lot of these larger gaps, and I was thinking, wow, it's just like moving different speeds, and that's not possible. But true to form, to any good observation, I'm holding the right to change my mind at what I think. Now we're going to skip down to the night of the 18th, which is the second row. And these, like I say, are pretty much hour by hour, not exactly, but they're close enough. We're just watching how far it's moved. It didn't move hardly at all there. And sometimes it seems to move a lot, and other times it doesn't move a whole lot. You can see these, there's a little bit of movement because it's blurry, and that's the indication we've got a little bit of motion clockwise. Normally, all I ever see is clockwise. And here we've got clockwise rotation. But then I see big gaps. I mean, the space between the two craters on the top there is much larger, and I think that's where we're getting backward and forward at the same time, which is making the gap wider. See, it's wider here. But this isn't that unusual here. When I overlay the two, then you're going to see what happens. All those were forward motions. Those were all clockwise, both days. Now I dropped it an hour back, overlaid the hour on the 16th backwards on the 18th, because we've 55 minutes per day the moon rises later. So I would say no movement there. It doesn't look like there's anything. But now we've got a counterclockwise. See, and the only way that's possible is that jump that Richard had, and probably another one the next day. And you see this is going to get progressively wider. And we're going, the 18th is counterclockwise from the 16th, which is on top. Isn't that interesting? Things they don't teach you in school. Now look at the gap. Here's where I thought the jump was. It might have had another one. But see, when I'm doing every hour, I'm not going to get those jumps. All I'm going to see is a wider gap. And the only way that's possible is either sped up or it's gone backward and forward. And that would explain it. If it had a jump backwards, that gap would be a lot wider. I think it's pretty consistently going forward in a clockwise rotation. Now I'm just overlaying the 2 days again, so you can see on the 18th, right there where I'm at, it was very little motion. It was still moving clockwise though. and I did the 16th. And it had quite a gap there on the 16th. So I hope you found that interesting. I certainly do. Now we're going to take the bottom row, and I'm going to move it 2 hours back and see what we get. I can't do as many because I'll run out of them now. I only had several hours. So I'll move those down, move the one in front of it over, which was already 1 hour back. And now we've got 2 hours back. Very little bit of motion there. It's blurry. Counterclockwise again. Excuse me. I'm trying to keep these in order because if I get them all mixed up, it's hard to sort out. Now here we go. I'll bring the hour. That's already an hour back. I'll bring it back again, and it's still counterclockwise. Now these are the 16th I'm putting over the top, and I'm bringing them 2 hours back and putting them over the 18th. That's a lot of backward motion. We still got quite a gap there between the Sea of Crises on the top, those two round craters. Now this will be the last one I can do because I didn't film that many or take that many. And look at that gap. And that's counterclockwise. Very fascinating.
Hey everybody, Rest, Mr. Thrive and Survive, February 28th, 2019. So in my last video, I showed our results from our first go around with trying to find moon rotation. And I will put a card up in the upper right hand corner here so you can look at that video. Very quickly here, we had two equatorially mounted cameras, which is the our side and the other side set. If you do that, you'll get no rotation. When we had a standard camera, just set on a tripod, and I just manually used that. The bottom line there is, if I blow this up here and try to center it for you a little bit, with all three cameras, we had the Sea of Crises up here at the 12 o'clock position, and by what was it, 7:20 whatever local time, suddenly the moon instantly, and I mean instantly, not gradually, instantly, with the naked eye and with all three cameras, rotated exactly 20 degrees counterclockwise. Didn't matter if you had an equatorial mount or not. There was absolutely no other rotation the entire night. Here is after the meridian crossing down here. It stayed the same in equatorial mounts, but you can see it started rotating rapidly to the naked eye and to the non-equatorially mounted camera. So I'm looking at a video, and let's go to that now. So this video here by World History Official, it's called Lunar Eclipse Solved. Eclipse on Flat Moon, Flat Moon makes more sense. And I'm watching this video, and at the near the very end of this 24-minute video, and I will have the link to this down below so that you can go look at this. We're going to start at the 22-minute 8-second mark, and this is during a lunar eclipse. There is no link below. I don't know what lunar eclipse it was. This was uploaded February 24th of 2019, so it could have been the most recent lunar eclipse. I don't know, but anyway, I would highly recommend you come here and take a look at this. But at the 22-minute 8-second mark, and I'm just going to play this normally here so you can see what happens. The moon will actually go black, and we're going to be interested in looking down here at this bright round crater, so to speak, right here, because the Sea of Crises, which is what we were looking at before, is going to be obscured in total black. But take a look at this, and this is a perfect equatorial mount, apparently, because this thing doesn't move. All right, here we go. So let's play this in regular speed, and then I'll come back and show this at a lower speed. Remember this down here. I'm going to put my cursor right there. Watch what happens. Get ready. Oh, what was that? Did you see how it rotated? This time it went clockwise. clockwise and instantly. Guys, these pictures are taken every 5 or 10 seconds. Now, I'm going to slow this down and we'll take a look at it again. Okay, this is 1/4 speed. I won't put my cursor on it this time. Notice how the shadow advances and then retreats, advances and retreats. Yeah, that's the Earth. Yeah, that's the Earth dancing in space. So notice that bright spot that we're looking at down there. And remember, it's when it changes and goes to the other way. Maybe I should skip ahead a little bit here, but we'll just let it play. Notice how the reds are much darker on the northern and western side of the moon. That's because the sunrises and sunsets on the northern part of the Earth had to be much richer that day because they were projecting a red shadow onto the moon. Ridiculous stuff, isn't it? So, here we go. There's that pulsating again. Earth dancing in space. Here we go. There's the white spot. Watch it now. Watch it. Here it comes. Here it comes. And bam. There it is. Explain that on the globe model. NASA's piece of crap model. So, the deal is, we hope to catch us again. It actually might be the 17th. I'm going to do a separate video. We need people all over the world to capture this. You don't have to have an automatic camera or anything that's automatic. You can take pictures every 15 minutes and manually do this because we proved that there is no field rotation, at least that we saw whatsoever, other than that 20-degree jump that happened instantly, even without a equatorial mount. So much more on this coming soon, guys. And there's been so many people now making videos saying we're not going to find any rotation, and if there is, it's field rotation, and that has to follow certain rules, and those rules are that the rotation has to happen pretty much at a steady rate, and we're not going to see it if we have an equatorial mount. This is an equatorial mount right here. And everything you're going to see here is before meridian crossing. This is, again, it started in daylight. All right, now what I did was, let me get to a darker picture so you can see what I did. There is a white crater that sticks right out here in the middle. I used that because that's the only one I could see visibly when I was doing the daytime shots, just to make sure we were matching. And I took an angle up to the Sea of Crises right here, and in fact this is the one I used as my base. So I use that. I'll make it so you can just barely see that little teeny speck of white in that crater right there, and then right through the Sea of Crises. And I took this line and just duplicated it. The exact same size and angle is throughout the whole thing here that you're going to see. So at 3 p.m., I know it's a little bit hard to see here, and this is as large as I can make it. Maybe in post-production I'll make this larger. You can see the right up in here is the Sea of Crises, and the line is actually going through the left, let's say 1/4 of it, or maybe even 1/10 of it. Most of the Sea of Crises is to the right. Again, this is roughly 3 p.m., the first shot we got through the clouds. And I don't know if you can tell here, but the very next shot is showing some slight rotation, actually. And they'll say that's too small to even measure. So, okay, maybe we don't have any. But now we're not on the left of the Sea of Crises anymore. We're right through the dead center of it. We're getting counterclockwise rotation, which would actually be the opposite of what we should see in the field rotation. So anyway, here we have this. And it's a pretty steady until all of a sudden here. And this jump between here and here occurred, let me see if I can get the time here, between 7:19 and 7:26, roughly. So in a less than 10-minute period, we got this much of a change. Suddenly counterclockwise. Then what happens? And we're still nowhere near meridian crossing. We have the exact same thing 45, 50 minutes later. Each one of these photos is roughly 45, 50 minutes apart, roughly. Exact same thing, no rotation anymore.
No rotation anymore. Maybe even just slightly more. Okay, there we are. And there we have the end of the night, or the end of when we recorded it. So this is even after the meridian crossing. We had 2 cameras that were equatorially mounted, and we had 1 camera that was not. So for those who want to deny that there's any rotation that we get, and field rotation, both sides agreed before this, guys, that if you do an equatorial mount, you'll get no rotation in the moon. Well, we've got it. Here's the most striking right here, and this was the most that moved in a very short period of time. So it's not even, which is what you would expect if they want to say it's a field rotation effect. It is not an even rotation. You get jumps, and this is what we've been trying to say. So they can come up with any kind of astronomical BS they want, and any kind of demonstration of what it should be, but these are the actual results. Now, are you going to take what we actually see, or are you going to take mumbo bumbo, you know, BS? And very compelling evidence is coming with the dissolving moon, Mr. Dazzle, the cameraman. Very compelling evidence to show you that, yes, the moon does disappear in the middle of the day without cloud cover and without its setting. It's crazy to me that people will not even look at the data. I kept saying the data is coming. Here's the very first part of it. Much more coming, guys. And as you're going to see, I'm going to describe field rotation first, and then we're going to take a look at examples of what this person in Germany also caught. And we're going to see it makes no sense as far as field rotation goes, because field rotation must follow a rule every time. It must do the same thing, and if it doesn't, something's wrong. Let's get into the video. Now let's look at some of the rules that we would have to apply for field rotation, because these rules would have to apply each and every time when we see the moon in the sky. Here I have a diagram where the moon would rise in the east, set in the west, and of course if we're in the northern hemisphere, the center or the high mark in the middle would be the meridian crossing, which would be to our south. So what we noticed was we have the moon here that rises in the east, and if you're going to say it rotates counterclockwise as it goes up like this, hopefully you can see the Sea of Crises here. It's rotated counterclockwise. Now I'm exaggerating some of these just so we would see how field rotation would have to work. Now this is what we've noted. It was actually pretty much from here to here we noticed a 20-degree counterclockwise rotation in the moon. So if that's the case, because it's rising, and then of course when we get up to the apex, it's still rotating counterclockwise till it gets to the meridian crossing. We get the meridian crossing, and then what happens is we get a rapid, much more rapid shift the other way. As you can see, as the night goes on, this is what we note each and every time. From the meridian crossing on, this is what we note each and every time. So if you're going to call that field rotation, then you can stick with the rules and that works. However, what we have noted beforehand is different. What we noted back here, looking at these two, the second and the third one, when the moon was in the exact same phase, in the exact same part of the sky, 1 month later, from February 16th to, I believe it was March 17th, give or take a day, we recorded the moon, and we got absolutely no movement whatsoever. In fact, from the time it rose until it got all the way up to just about the meridian, we were recording, and there was absolutely no rotation in the moon. Again, the exact same phase, same part of the sky, same degrees above the horizon, and we got no rotation. And we got no rotation again on cameras that were equatorially mounted. Now remember, when we first caught this rotation counterclockwise on the second to third position in the moon here, we got that 20-degree rotation almost instantly, and then for the rest of the night until we got meridian crossing, we showed no rotation whatsoever. And even after meridian crossing, in the 2 cameras we had set equatorially mounted, there was absolutely no rotation. To the unaided eye and to a standard mounted camera, we got the traditional rotation clockwise. So if you're going to claim field rotation, that's okay, but it has to follow the same rules every time. And what we're seeing is, when we're at this part of the cycle right here,
Sometimes we get a rotation counterclockwise, and sometimes we do not. It's got to follow the same rules every time if it's field rotation, and it does not. And I can't rule out that this is the same every time either after we pass meridian crossing. Is it the exact same amount of degrees that it rotates each time? And it is much more rapid as soon as it gets there. So why is the first half showing either 0 or counterclockwise rotation and the second half showing clockwise rotation? So if you're going to say this is a field rotation thing, it's got to follow the rules, and we already know it's not following them pre-meridian crossing. Okay, we're going to take a look at two different videos here. I'm just going to start playing this, and when we get to the part where I want, we will get there. This is going to show the what I just showed you with the field rotation. It's going to show you both before and after the meridian crossing, and it's going to show a counterclockwise sudden movement just like we found. And this is thanks to Gutasaken in Germany. And I'd like to thank him for permission to use these videos. There will be links to these two videos down below, and I'm not going to play this all the way through. I just wanted you to see the different things he's showing. Now, he does have different sizes of the moon, and I have, as you will see, taken two of the ones I want to particularly look at, and I have made them the same size, and I have also changed the contrast so we can see it a little bit better. But you can see there's both small and large jumps in the moon here, and some of them are very large in a very short period of time, and some of them are a little bit in about the same period of time, sometimes longer, and that doesn't make sense with field rotation either. It would be a steady rotation the whole time, and that's not what we see, and again, we don't see it every time. So what I want you to see here is coming up, and this is at the, when you come to this video, it's called Centered Photos of Rotating Moon, January 14th to February 20th, 2019. So it doesn't look like I'm the first person that caught this, or the only person in the history of the world that has ever noticed this. Here we go. We are at the 1 minute 31 second mark. The Sea of Crises is right here. It might be hard to see. And note the time, it's 16:24, and guess what? This was the day after I caught the field rotation, me and Mike Ball, on February 16th. So this is 16:24. Now I want you to see the next photo as it gets there. 16:45. So in roughly, what, 20 minutes, 21 minutes, we have a counterclockwise rotation. If you didn't notice that, you will see it here. Here it is. Again, they're different sizes. I fixed all that coming up. So let's go ahead and take a look at that right now. Alrighty, here's the two photographs right here. Let me go ahead and zoom in a little bit. You can see 217 at 16:24, and the other one is a little bit more readable, 217 at 16:45. So in 21 minutes, we have a rotation between the two. Now what I did was I took these photographs and I made the image appear to be the exact same size in both. Let me drag this down just a little if I can so you can see it. Now you should be able to see with the naked eye that we've got rotation in 21 minutes counterclockwise, at least 20 degrees. At least. This is probably even bigger jump than what we caught. And again, in 24 minutes, let's see what it looks like when we drag this over. Going to the center again. Whoops, sorry, grabbed the wrong one. Just grab this, come down to the same area. What do you see? That might be 30 degrees rotation, 25 to 30 in 21 minutes. So we're going to catch this thing even in shorter time periods. We have it down to a, what was it, a 16-minute time period or even less that we caught this. So we're not the only ones catching this. Not at all. Now let's take a look at the other video. Alright, this one is called Rotating Moon 180703, Christmas Keys. Again, Gutasaken is the same channel. And we're going to play this, and he asked the question right away. Does the moon rotate? So I'm the only one in the whole world that's ever noticed this, huh? See where it is, Western Germany, Rhineland. That's important. I'm going to show you Germany a little bit. So he's drawing a line across one of the other seas, and he's showing you that line, and it's 1:56 a.m. and now 2:01 a.m. on July 3rd, 2018. And he's got a few other photographs here. Oh, look, 3:31 a.m. What do we have? Counterclockwise rotation. The red on there is the orange. So look, moon rotated several degrees counterclockwise within 1.5 hours. Okay, so this is a phenomenon that has been noticed by others, and this is something we have to investigate. And I started this whole thing by saying the shadow moves with the moon when it rotates, which means if it rotates that fast and at different paces over the same period of time, it can't always be pointing directly at the sun unless the sun suddenly did a jump in the sky. So let's take a look at a couple things here. I want you to see where in the sky we saw the lunar jump on February 16th and the time. So this is within 16 minutes roughly of when we caught it. Here's where it was in the sky. Then the next month, here we go, and we recorded it from about here, actually from about moonrise, all the way over to about here, and absolutely no jump. Same part of the sky, absolutely zero rotation. Same cameras, same equatorial mount, everything. No rotation, whereas on this date, we get rotation of 20 degrees within 16 minutes. So let's take a look at some of the Germany ones. Now what we're going to take a look at is these pictures right here that were done on February 17th of 2019, the day after we caught our leap. This was done somewhere between, again, a 21-minute period, 1624 to 1645. So we look at mooncalc, we have Germany, 17 February at 1630, right between the two. And what I want you to notice here is how much earlier it is in the path when it jumped. All right, now we noticed nothing through this part until we got here. Now this is going to become even more apparent with the last series that we're going to take a look at. Okay, the one we looked at on July 3rd, 2018 at 03:31 a.m. Let's take a look at. There you go, you can see the date there and time. So let's take a look at that and where it was. And guess what, guys? I haven't covered every single one of the counterclockwise he's gotten. And this is during the waning phase, not the waxing phase, the waning phase. And here it is on mooncalc.org. Look how close we're getting to meridian crossing right here. Here's meridian crossing. We're not very far from that at all. Much higher in the sky. So this is a phenomenon that happens apparently at random times. I'm waiting to catch it over here past meridian crossing, although I doubt I will. We're going to get this clockwise, very rapid every time, which makes no sense because you should have a mirror image over here. And sometimes, again, you have nothing going all the way up to meridian crossing, then a rapid rotation. Other times you have counterclockwise, and I'm sure we're going to eventually catch clockwise on the side too, perhaps. But it follows none of the rules of field rotation. This can't be explained by that. The moon jumps, and it jumps counterclockwise, and that cannot be explained in NASA's model. And those are the facts.
Today I'm going to point out a little known fact that throughout the day the moon rotates about a half a turn clockwise and counterclockwise, and the light and the dark side and the moon all move in unison as one unit, irrespective of the location of the sun. And that's why sometimes you'll see that it appears the sun is casting light on the moon, and then other times the angle will be way off and the sun will be pointed toward the dark side and the opposite side will be lit up. And that's because the moon moves as one unit with the light and dark side, and it doesn't matter where the sun is. I'll tell you how you can prove this to yourself by taking 4 pictures in the daytime of the moon and paying attention to the light and the dark side and the texture of the moon. It all moves as one unit. I wanted to talk about angular problems between the sun and the moon. Lots of times I see the moon and the shadow or the highlight, and it's way, way off from lining up with the sun. I live on the west coast of the United States, in Oregon, in a small town called Coos Bay, and it borders the Pacific Ocean. So I have a great view of the sun and the moon out over the ocean. The other night I was sitting on the back porch having some coffee and looked out the window, and the moon was headed down toward the horizon, and I could see it was way, way off from what it should be to line up with the sun, which had already set. So I called my wife and I said, "Hey, come here, I want to show you something." And so she came out and took a look. I said, "What's wrong with the angle of that moon?" And she said, "Well, the sun has gone down beyond the horizon right below the moon there." And I said, "No, it hasn't." I said, "In the summertime it sets right there." I said, "But in the wintertime it sets southwest. So that's way off." And she said, "Oh, you're right." So I went in and grabbed my Nikon P1000 and took this photograph that you see here and the video that you saw before that. And that was on January 13th of 2019. The next day I went out to the Cape Argo lookout and used my Theodolite app for my iPhone and got some readings for the sun set and for the moon. With those readings in hand, I'll try to give you a better perspective of how far apart the sun and the moon were. The sun was at south 64 west and the moon was at north 89 west. So essentially we have the sun southwest and the moon was due west. So now I want to show you what bothered me when I was sitting there looking out of my window drinking my coffee. Look at this moon and look at the angle to the sun. It doesn't work out very well. In this visual representation of the angle of the moon and the sun, I clipped the moon right out of the video that I took of it, so the angle is right. Of course, this is just a visual representation, so you can get the idea of what I'm talking about. A lot of people don't realize that the moon rotates back and forth, and like a clockwise and counterclockwise. And when it rotates, the moon, the shadow, and the highlighted side all move simultaneously. And you know, that's why we see such wild angle discrepancies between the moon and the sun. And this happens on a daily basis. Throughout the day, in one day, if you have a clear sky, you'll see the moon do almost a half turn. And by the time it's done, it's not pointing toward the sun at all. And if the sun were causing the highlight and the shadow on the moon, you would see the craters and everything move, and the shadow would stay fixed, and the highlight would also. Here are the two photos I took both in the same day, and look how much that's turned. And if you look at the craters, they've all gone right along with it. So that highlight and that shadow are not caused from the sun at all. Here's another set of photos that I took in December of 2018. And look how much that's rotated in the same day. This happens on a regular basis. It's quite an angle shift. I can see some of the craters on it, and they went right along with that highlight. This is my backyard, and I went ahead and put side by side where the sun sets and where the moon was setting on the day that I was drinking coffee, and noticed that the moon highlight was facing north and the sun had set in the southwest. Look at the angle of the highlight on that moon and explain somehow, if you can, how the sun is casting that highlight on that moon. I don't see how it's possible. Yeah, if you put the sun right down here to the right, that's where my wife thought it was setting. And I told her, no, it's setting down southwest. So let's play around. I'll put the sun right down where it should be. Now, doesn't that look a lot better? It could actually light that side of the moon. I can't see how, well, if the moon was transparent, the actual sun might be lighting that side, or it might be reflecting off the dome or something. Now, I know people are going to come back and say, well, you don't know calculus, or you don't know physics, you're a moron. Well, what kind of a moron would I be if I thought that actual sun was casting that highlight on that moon at that angle? I would have to be quite a moron. Well, it's not casting it, not at that angle, it's not. It's an easy thing to do to prove to yourself that the moon is rotating and the shadow and the highlight all simultaneously, just on a clear day, not at night. Take an early morning photograph, take one at around noon, and take one around evening, and you'll see that that's all of it's rotating. And then pay attention to where the craters and stuff are. Here's the theodolite that I took as the moon was headed down for the horizon the day after I saw that it was tilted wrong. And this is the sun theodolite that I took on the same day. And for those that like numbers, here they are both side by side. So what have we learned here today? We've learned that the phases of the moon, the light and the dark side of the moon, and the moon itself rotate independently from the supposed cast light of the sun. We've also learned that you can easily prove this to yourself by taking 3 to 4 pictures throughout the course of a day and putting those images in your computer by time and analyzing that the light and dark side move in conjunction with the craters on the moon, and that this all happens independently and irrespectively of the location of the sun. Today, I'd like to talk about some observations that I've made over the last couple of days while recording the moon. I started out just taking pictures every hour or so of the moon and doing comparisons. Then I decided to go ahead and start doing a video recording between the photo shots that I took. And I want to tell you what I saw when I looked at the video recordings. First off, I was able to capture another one of the backwards rotations of the face of the moon. And secondly, I was able to detect the motion of the moon as it crosses the sky, that it moves at variations of speed, sometimes fast, sometimes slow. And I think I can confirm that. So it just appears everything that they've told us about the moon just continually appears to be wrong. it's possible that these speed variations that the moon has as it crosses the sky, it's possible that that's a product of a very close and low altitude moon coming toward us, crossing our vantage point, and then going off into the distance, and you might see variations in speed because of that. Okay, here's my random speed test. I just took random clips out of the videos that I've taken and started the moon right at the beginning on 0 on both of these. And again, these rulers were adjusted side to side horizontally on each screen, so they should be the same, same size. Now, I've done quite a few of these. Like I said, I had like 30 minutes of them, and sometimes they're exactly the same speed, but other times, like this, they end up being about 1/8 of an inch is about standard for the variation of speed. But if you take any one of these pictures, the daytime one or the at dusk, and you duplicate it and put the same ruler set up here, it ends up exactly on the dot. So I can tell that the speed is right, and the ruler is correct also, because otherwise it would be off also. But so we're seeing in about 1.5 to 3 minutes, because none of these are any longer, but I have to keep adjusting my screen on my camera to as the moon moves off the screen. So it's only on the screen for about 1.5 to 3 minutes, depending on which angle it's going. But you can just watch this and see for yourself that these are going at different speeds. And I encourage all of you to get out and try these things for yourself, because we're finding evidence of something vastly different than what the schools and the astronomers and stuff are telling us. Speed variations are a major thing. That moon, when it went backwards, the Sea of Crises moved backwards. The Sea of Crises is about 315 miles across, so they say. So that would translate down into about around 150 miles. That's not insignificant on the surface of the moon. And if the moon is smaller, it doesn't matter. It's still moving backwards. So it can't do these things in the heliocentric model. And I don't know what to make of it all. I don't think NASA even knows how the moon functions and stuff, and I think it frustrates them. And so they make up a bunch of garbage because they don't want to sound like they aren't all supreme and know-it-alls. They want to be godlike. But you'll find that these break down into about 1/8 of an inch of difference. And like I said, I had a lot of them that were the same. But at these times when I did random clips from my video, I found quite a few where the variation of speed was different. And also on the same day. Okay, I'll just let these play. If you want to review them, you can skip forward and look at the results of each one. If not, then I think this is good for this video. Have a darn nice day. So I just want to add one more thing here. Just remember that these aren't over 2 or 3 minutes long, and some are only 1.5 minutes. And if we're detecting that much variation in speed, given more time, that speed would be more significant. We're just getting a short, very small snippet of the travel of the moon in these, and it's still detectable, meaning that it's actually a major thing over a vast distance. Just wanted to point that out. It would exponentially get to be a greater distance between the slow and the fast moon.
Watch what happens. Get ready. Oh, what was that?
Hi, Blue Fox here. On September 27th, 2015, I took pictures of the eclipse of the moon. I set up my 5-inch telescope using a 17mm eyepiece and took these snapshots. You will notice in the pictures, stars show through the dark portions of the moon. And as I go through them, I'll blow them up a little larger so you can see these stars. I'll point to one. There's a blue star here, a white star, there's another star right here that shows up quite good, and that's that picture. Move on to the next one. You can actually see the stars here. Now we'll zoom in and we'll see a red star with a white star right in here. And then there's 3 stars, a white star, a blue star, and another blue star. And there's a white star pretty much over here. Okay, now this one here, you can see the stars. 1, 2, that's pretty bright. And I'll zoom in on it. Now there's a red star, white star, showing through the moon, white star, and then a blue star again, with another star over here. And as we go further down, we see another blue star and a white star. There's more stars that I'm picking up on this film. They do have 2 stars out here on the edge, but this is basically closer to the left side of the moon. Moving on, you can see 2 stars here. There's another star here, 2 stars down the bottom, and another star here. So we'll zoom that up for you. There's the one on the bottom. Some stars shining through. And there's another 2 stars. Faint one in the background. And we have this star, blue star, and this white star. Also we have 1 star shining through here. And we look at this, we see the stars shining through again.
This is what we're taught in school. The Earth is rotating counterclockwise, and the Sun is stationary, and the Moon, for all practical purposes, is stationary as well. So let's take a ride in the car and see how this works. The distant mountains would be the Sun, and the trees that are coming by would be the Moon. What do you see going on here? What you see is the Sun lagging behind, and you would see the Moon overtaking the Sun. And that's completely opposite of what we actually see in reality. Everybody has been outside and they've seen the moon rise, they've seen the moon being overtaken by the Sun and setting. And if you haven't, you need to take another look.